Dear student, I am Dr. Harold Thomas, Professor in Geology, Dr. Harish Gaur Viswadhyalaya Sagar. Today, I will deliver my lecture on limits of metamorphism. I will cover this topic in two parts. In part 1, I will proceed under the following heads: limits of metamorphism. Hope it will be useful for you. Try to be regular in course. We already understand the process like weathering and erosion. The process of weathering, cementation and diagenesis are the primary process for the formation of sedimentary rocks. Weathering is the alteration of rock at or near the earth's surface by atmospheric agents. It involves the physical disintegration and chemical decomposition of rocks and produce a mantle of loose waste or soil. These material later on transported and deposited into geosynclinal basin, then through different processes merge into sedimentary rocks or form sedimentary rocks. The limit of metamorphism are considered in terms of temperature and pressure. The general temperature condition of formation of metamorphic rocks lie between those of sedimentary rocks that form at temperature below 150 degrees centigrade plus minus 50 degrees centigrade at atmospheric condition. For these processes, the temperature nearly 150 degrees centigrade or so that we can decide the lower temperature of metamorphism is the process that is close to diagenesis, because at above 150 degrees centigrade and 300 megapascal pressure, the diagenesis process is merged into metamorphism, and below this temperature metamorphism cannot take place. Since rock of diverse composition take place in metamorphism, the low temperature limit would be vary with the composition of the parent rocks. Mayasiro in 1973 placed the lower temperature limit of metamorphism at approximately 150 degrees centigrade, but large scale mineralogical changes occur at temperature above 250 degrees centigrade. Metamorphism by definition take place essentially in the solid state. The temperature at which rocks begin to melt would define the higher temperature limit of metamorphism. However, this does not mean that rocks containing a small quantity of melt fall outside the preview of metamorphism. The migmatites contain two or more petrographic units, one of which is the result of crystallization from a melt. Melting temperature of rocks are dependent on composition, pressure and the presence or absence of fluid phase. At 1 bar and under wet condition, granite and basalt begins to melt at 950 degrees centigrade and 1000 to 1100 degrees centigrade respectively. Yoder and Telly 1962. The granitic belts that develops in rocks undergoing metamorphism at high temperature more than 700 degrees centigrade plus minus 50 degrees centigrade. At depth at 10 kilobar, granites begin to melt at 650 degrees centigrade. Brocher and Wiley 1968. And temperature of beginning of melting of basalt at this pressure is close to that of the granite. Peltic rocks begin to melt at temperature slightly higher than the granite melts, thus allowing for a range of 0 to 10 kilobar in the continental crust. The high temperature melt limits of metamorphism can be presumed to lie the range 700 to 900 degrees centigrade. Especially granulites documents temperature around 900 degrees centigrade and define ultra high temperature metamorphism UST. The large changes in pressure with increasing metamorphic temperature define the limit of metamorphism. The IUGS has formed a sub-commission on the systematic of metamorphic rocks SCMR following the example of the successful igneous subcommission in an attempt to seek agreed upon the standard metamorphic terminology and concept. There is a general consensus that metamorphic begin in the range of 100 to 150 degrees centigrade, and for the more unstable type of protolith and may be marked by the formation of minerals such as lomentite, analcine, hollandite, carfolite, paragonite, prehenite, pumpelite, lawsonite, glaucophene or stiplomelain. Some geolites are considered diagenetic and other metamorphic. At the high temperature end, the metamorphic processes are merged into igneous process nearly above 1000 degrees centigrade. The limit of metamorphism within the earth crust are not sharply defined. This is because the boundary between the high grade metamorphism and magma formation by rock melting on one hand and that between diagenesis and low grade metamorphism on the other is not sharply distinct. The mixed rock, which is known as migmatite mixed rock, that occurs at where high grade metamorphic rocks subjected to partial melting and merge into igneous rocks. Beginning of metamorphism cannot be easily demarcated from the diagenesis, in which recrystallization is implied by reduction of sediment porosity as a result of compaction. Diagenesis related to dynamics of sedimentary basin which precede or accompanying orogenesis. Thus, it is hard to distinguish between beginning of metamorphism and the end of the diagenesis. However, elite crystallization give idea of diagenesis and metamorphism. Elite is an alkali deficient muscovite having less substitution of alumina for Si and having more water. Thus, elite is precursor minerals of muscovite. So, change of elite to muscovite is a measure of the degree of diagenesis and very low grade metamorphism. Recrystallization called NHE metamorphism, that means the beginning of metamorphism. In this lecture, I will proceed under the following heads: pressure limits and summary. Hope it will be useful for you. Try to be regular in course. The pressure limit of metamorphism are also fairly broad. Metamorphic process also take place with certain pressure limits at low pressure, and an abnormally high geothermal gradient may be required to heat rocks sufficiently to initiate metamorphism, which increase the temperature so that rock can metamorphose. Similarly, at the contact of intrusive body, the normal geothermal gradient is high and pressure is low, so that in this case contact metamorphism occur, or some metamorphic rocks such as those crystallized around igneous bodies may form at near surface pressure. The pressure at the surface of the earth is 1 atmospheric, which is force exerted by the mass of the atmospheric pressure. Pressure is calculated by the relation P equal to rho Hg, where rho is the density of the exerted body, H is the height which is equal to 76 centimeter of mercury, and G is the acceleration due to gravity, that is 9.8 meter per second square. On the calculation, we can get 1 atmospheric pressure equal to 13.6 kg gram per meter cube into 9.8 meter per second square, and 0.76 meter equal to 10.12928 kg meter per second square on that, or that is 1.01 bar. On the other hand, solid rock extend through the extensive mantle samples are exposed in ophiolites and comprise the uppermost mantle beneath this oceanic crust, initially 10 to 20 km deep. Metamorphic of solid rocks occur at higher pressure due to the load of overlying rocks column. This pressure is called lithostatic pressure or load pressure, that is P load. At greater depth, regional metamorphism occur at several kilobar. For crustal rocks, load pressure can be easily calculated. We want to calculate, then we have to take the equation for the rock column. For example, like granite, basalt or pedrotite, we know already the G equal to 9.8 meter per second square. If we know the height of the rock column, then we can calculate the pressure on a surface. For example, the acceleration due to the gravity near the earth's surface is small g equal to 9.8 meter per second square, and the range of typical rock density are granite 2.7 gram per centimeter cube equal to 2700 kg per meter cube, basalt 3.0 gram per centimeter cube equal to 3000 kg per meter cube, pedrotite 3.3 gram per centimeter cube equal to 3300 kg per meter cube. Using these values, a 1 kilometer column of a rock exert a pressure of granite P equal to 2700 kg per meter cube into 9.8 meter per second square into 1000 meter equal to 264 into 105 Pascal equal to 264 bars. Lithostatic pressure is exerted by the overlying mass of the rock, and its magnitude depends on the depth and the density of the rock column. Knowledge of the depth lithostatic pressure is of paramount importance in making tectonic reconstruction. The relationship between pressure and depth in the crust is given by the equation where P is the pressure, rho is the density of the rock column, and H is the depth. SI conversion for the unit of pressure is the Pascal, where 1 Pascal equal to 1 kg meter per second square. Geological pressure has been traditionally reported in bars or kilobars, and the conversion is 1 bar equal to 105 Pascal equal to 0.1 megapascal or 1 kilobar equal to 0.1 gigapascal. The acceleration due to the gravity near the Earth's surface is G equal to 9.8 meter per second square, and range of typical rocks densities are granite 2.7 gram per centimeter cube equal to 2700 kg per meter cube, basalt 3.0 kg per centimeter cube equal to 3000 kg per meter cube, pedrotite 3.3 kg per centimeter cube equal to 3300 kg per meter cube. Using these values, a 1 kilometer column of a rock exert a pressure of granite equal to P equal to 2700 kg per meter cube equal to 9.8 meter per second square into 1000 equal to 264 into 105 Pascal equal to 264 bars. Pressure is defined as force acting equally from all directions. It is a typical of stress called hydrostatic stress or uniform stress. If the stress is not equal from all directions, then the stress is called a differential stress. If the differential stress is present during the metamorphism, it can have a profound effect on the texture of the rock. Minerals that crystallize or grow in a different stress field can have a preferred orientation. This is especially true for the seed silicate minerals, the micas, biotite and muscovite, chlorite, talc and serpentine. Dear student, today in this lecture we have discussed about the limits of metamorphism, part 2, I have covered this topic under the following heads: pressure limits and summary. I believe this lecture was useful for you. For further readings, please read the textbooks, references and links given in the text. Thank you very much.